Welcome to another Rigonomicon.com video. Today I have something very interesting. For a number of you, this might be a very simple video where you'll stop after a couple minutes because you'll get to the answer that you're looking for. But for the rest of you that are curious and want to know more, this is actually a very important video because we'll be able to use what we're learning here for an aim constraint to be able to do more complex things. And it's really the introduction of what the transform matrix is and how we can use that. All right, so first off, this is a new version of Rigonomicon, and I had to test it because of the release of Maya 2027. So because of that, I got Linux back up and running, and I'll be running everything on the Mac as well to make sure there's a version for everybody. And everything works fine. In fact, all the tools, the new updates I've done are working in Linux, and I was doing it only in Linux just to see how the workflow was, and even the video editing and all that is being done in Linux. So just to see, what kind of problems I could have, and it's been a good run. For those of you that are on the Autodesk forums complaining about Maya not working in other, like the Linux that you like, I'm just going to say this. You can fight it all you want. Autodesk isn't going to help you. They've proven it time and time again that Maya doesn't need to work on, it's not going to work on Debian. It's not going to work on a lot of things. So, and forget about, Wayland and all that stuff. If you want Maya to work, you're going to need, and you want to use Linux, you have to use a Red Hat Enterprise version, so either Red Hat or Rocky Linux for the rest of us that don't have the money for Red Hat. So Rocky's fine. It's basically it's just as good as Red Hat, and it is supported by Autodesk. So if you want to talk to my cat is being a real bum. Hang on a second. Okay, so so here I have a screen where I have Rocky Linux up and running. I'm using Rocky Linux 9.7. As of 2027, you need to have that version of RHEL, and you should be fine. It works fine. Everything's good. I haven't had a single problem with it. So don't fight stupidly trying to make it work on the Linux that you want. Just make it work on the one that Autodesk has support for it. If not, it's a ridiculous waste of time, honestly, and I find it very strange. So, for those of you that are doing this as well, just know that I'm using 9.7, and that's it, and that's all there is to it. Okay, so let's move on. All right, so we're going to be talking about the aim constraint today, and the first thing I'm going to do is I'm going to talk about Maya's aim constraint in particular. And for some of you, that's all you really want. You probably hit the problem that many people hit, which is they use an aim constraint for the eyes in some way. They probably had some sort of controller up front, and they figured just having the points that the targets for the eye to aim at is good enough. And then they realized, oh, wait a second, there's something going on where the eyes are spinning in a weird way. And I'm going to show you how to use Maya's out-of-the-box tool to be able to fix that. But I'm also then going to explain if you're using the Rigonomicon tools, which are free, there's no reason why not. And I'm always updating it with every release of the new every new Maya. So you really have no reason why not to use the bacon look at that's there. And I use the term look at because you aim guns, you aim darts, you aim the concept of up doesn't really make sense, but a look at is inherently suggesting eyes or something of that nature. And when you're looking, there is the concept of, not only the target, but also where is the up. So I generally use the term look at, or in video games, we also use the term billboard. A billboard is like particles have billboards. So that effect means that it's looking at the camera all the time. So imagine you're driving down a road and you see a billboard. It's aimed at you, not at the cows in the pasture. So that's why we use the term billboard as well. So this is the same thing, and we can use this for more than just having eyes look at objects, but it's generally what we should be using it for. Hopefully some of you remember the video that we talked about how to use an aim constraint in Maya for wrists, for basically having to do a twist bone or roll bone on the wrist. And that's kind of a hack of the aim constraint. And you're going to see that the Maya constraint itself is not using terminology that's very easy to understand. And it'll get you. Every once in a while, you'll go back and you go, oh, yeah, that's what they meant. So the Bacon Look At is going to be a simplified, cleaner version of the aim constraint for Maya. And it's been made to be as optimal as possible and to really take advantage of all the modernizations that Maya has while still maintaining its architecture. So I am not reinventing the wheel here. I am building it exactly the way it's supposed to be built for Maya's architecture. I'm also going to explain a little bit more in the node editor so we can see what's actually happening under the hood and what Maya is actually hooking up. So you got to remember there's the plugins and the constraints and all that, and then there's the interface, the thing that you use to tell Maya, build me a node and connect these things for me. And you're going to find that sometimes it's doing a lot that you don't want it to do. So I'm going to go over that real quick, and I'll show you how to just be able to connect things yourself, so you don't have to always be at the mercy of the interface. Then I'm going to talk about cross vectors, because to understand what an aim constraint is actually doing mathematically, we need to understand cross vectors before we even get to the transform matrix. Because the transform matrix, how are you going to construct one if you don't even know what it is, and how a cross vector is going to help you for that. So I'm going to go over cross vectors and transform matrices in a very rudimentary way so that we at least understand what we're trying to do and how cross vectors help us. Cross vectors are a very basic functional thing that we need in math all the time, and you're already familiar with it when we did the right-hand rule and a couple of other things. So if you remember that video, please take a look again. I explained it in detail what the right-hand rule was, and that was helping us determine rotations. Hopefully some of you still remember the gimbal space and how we can have gimbal locks and all that stuff and how we can avoid it. That's all I'll try to do as quickly as possible. I'll go over that. And also I'm going to introduce, we're just going to peek into, or we're going to look at some C++ code that this time around, so I can start introducing basically the structure of a file and how we build those tools, because Bacon Strip is the core plugin tool set that I've been building, it's open source, so you can just read it, you modify it, you can build your own. But the most important thing about it is that if you wanted to, you could learn how to make your own plugins that solve your own problems, and that's kind of the idea of what the Brigonomicon is all about. Okay, so just to go through, this is what we're going to go through. For some of you, you may have come here just for the, hey, I need to fix this rotating eyeball that's weird. Point 1 is going to be just fine, and you can move on. You'll have it on in the description, so you can jump to it directly. Okay, so here we are in Maya 2027, and I've already set up a little scene. There's nothing much going on here. As you can see, there's very few objects. I've gone ahead and made some shapes so we can see axis directions and know which axis is pointing to what. This is obviously like the worst character in history. It's just cubes for, like, this is the head, this is the neck, this would be the left eye and the right eye. So we're actually going to hide these, and we're just going to focus on this one right now. And we're going to talk about, the reason why I colored them is because we need to really lock down how things are behaving and in what order things get set up with which options that are in the aim constraint for Maya. So I guess the first thing we're going to do is we're going to open up the node editor. So I'm going to put that over here while we're working so we can see what's going on. And we're going to see our result over here. I'm going to select this and this. If you have something here and you want to get rid of it, just press I like to call it the Etch-a-Sketch. I don't know if you know what that is, but it's a thing that you would shake and the image on it would disappear, and then you could use the knobs again to draw something on it. It's an old toy. You click that, and it'll just clear out the screen. Now you have nothing there. Now we can start working on things. And these plus signs are just going to take whatever you have selected and either add them or remove them from the little viewport we have here for the node editor. So the eye is the thing that we want to affect. So it's going to have inputs. I'm going to press 4. If you don't have anything set up for 4, just press 3. That's good too. Also, you can press these buttons at the top here. For the number 4, which is over here. Yeah, actually, I don't know if they have the button for it. But anyways, if you press 4, and it'll bring you to a special one, whichever one you've set up. And I've set this up beforehand. And it's not hard. You go into Edit Custom Attributes List, and this will affect every object that is of this type. So in this case, it's just a normal Maya joint. There's nothing special about it. And you can pull out whichever things you want to use and remove the ones you don't use. And then once you're done, you just click Edit. It's done. And then from then on, every object that is of that type will also have that there. So I'm just going to set these up. So we have the target. The target is going to be affecting the eyeball, which needs to have, we need to know, we're going to be paying attention to this green part of the eyeball to know where the up axis or the y axis is pointing. And, you know, like if you've hit this problem before, it happens all the time. You don't set up the up axis correctly, then the eyeball does weird things and it will spin. So we need to lock it down. And this is just an object. It's just a normal target. For now, it's not part of anything. It's just a thing for the eyeball to look at. Okay, so the other thing I'm going to do is I'm going to pin these so that when we start adding stuff, it's not going to go all over the place and change the window. It's just going to be locked down to these 2 spots. Okay, good. So normally what you do is you just select this, and the Maya architecture and basically every tool in Maya is designed to select things that are going to be affecting your object. And then the last thing you select is the object that's going to be constrained and have the constraint and all that. That's normally the order in which you select things. So I'm trying to maintain that logic. And what we're going to do now is I'm going to use the Maya version. I'm just going to press spacebar. I don't need to mess around with all that because I can just go straight here. And we want an aim constraint. And I'm going to go to the options. So now we have the aim constraint window. And now I'm going to go through them. I'm going to show you what the differences are for each one of these. And we're going to understand what's going on. So the first thing you want to do is turn off the maintain offset. We don't need to worry about offsets right now. Offsets is basically going to say, I'm going to have a constraint, and then I'm going to always include this difference from the moment where we created it. So if I have, like, let's say I wanted this constraint to aim at this, but then always have a rotation that's like over there, but it's still aiming at this, like as if it was still here, type of thing. You can make it so that it maintains that little offset while still behaving the way you'd expect. For this, absolutely just remove it. We do not need offsets. It's just going to confuse you more. We don't need it at first. Later, we can investigate and see what it is. The first thing I'm going to ask you, though, what do you think the offset is? Is it going to be a position or a rotation? So because we have the XYZ here, but we don't really know what kind of an offset it is. And I'm just going to let you think about that. So we're going to ignore this, and I'll come back to that later. Animation layers, we don't need to worry about any of this. For what we need, this little line here is basically saying everything above is extra. We don't really care. What we really care about is what's in here. This is the main section that we need to worry about. So the aim vector is going to be the vector of the object that you're trying to affect, and we want to know where it's aiming along. So in this one, hopefully you remember our rotation order and our rules to best serve us when it comes to rotation. Because we're working in Maya where it's primarily Euler across the board, it's nice for some things, but it's also terrible for others. And if you've ever had gimbal lock, you know what I'm talking about. And I go into a great deal of work in other videos to explain how to avoid gimbal lock as much as possible and to to really make your rig as strong as possible to avoid those kind of issues, and while still maintaining the Maya approach of XYZ Euler rotations. Okay, so I should be saying Euler, but anyways, it doesn't matter. I just call it Euler, like the Edmonton Oilers. I guess I'm a little too Canadian. Okay, so the aim vector is going to be the x-axis. So unfortunately, Maya likes to put numbers that you can type. And yes, it can be useful, but it's also a pain in the butt whenever you want to have something that doesn't point on an axis, or which is rare. But it's like, what are we really doing with this? It's like, why couldn't we just have X, Y, Z and then have maybe something for, flip the axis? So already we're starting off on a bad foot here. It's for the aim vector, we have to type 1, 0, 0 for the x-axis. It's not a big deal, but it's still kind of like, okay. And it's going to aim in that direction. Okay. The up vector, the one that's being referred to here, the up vector is the one of the object. So it's going to be what it's going to use as an up vector here. So if we wanted to, we could have said the blue one's the up vector, so that the Z points up, and if it had been that, we would put 0, 0, 1 because it's X, Y, Z, right? So, but in this case, we're going to leave it at 0, 1, 0 so that the yellow vector goes up. The one thing you don't want to do is make it the same as the aim vector. That is a mathematical no-no. That's code 16. The problem is 16 inches away from the screen. You want to have a different vector, a different axis to be using. And remember, the up vector is not an absolute vector, and we'll go into that in just a moment. It's just a suggestion of where you want the up to be. It still has to maintain an orthogonal axis. Orthogonal axis means each axis is 90 degrees from the other. There's none of them that are at 30 degrees or 40 degrees. And we're going to get into that later, why that's a bad thing if we did have something that was 90 degrees. So even right off the bat, Maya gives you the opportunity to really break that 90 degree thing right here. But the up vector you want to have pointing up, so 1. World up type. This is the thing that it's going to use as a reference to align this up vector as best as possible. But it's going to prioritize the aim vector. It'll never deviate from the aim vector. It's always going to work. What the up does is it kind of tells it, I want it to point in that direction in general. Okay, so what is it going to use as a reference? And we have a pretty long list here of things. I'm going to use scene up for now. You're going to notice everything gets grayed out. In this section here for constraint axes, I'm just going to turn it on for a moment. I'm going to do X and Y, and that's it. I just want to see what happens. And now I'm going to select it in the right order, right? Always the thing that you want to affect last. Press apply, and it creates this. Oop. I just want to select this, and then I'm going to press 3 in this case, because I just want to see everything we can. Okay, so I did X and Y. I didn't constrain. I didn't say all of them. All this does down here, and that's why I'm doing it really quick here. It's just what it's connecting. It's not doing anything fancy. It's really stupid. It's just doing X and Y. It's connecting the lines. Here you go. This is what would happen if I'd put all 3 of them. And yes, you could use this as a hack for the wrist, the twist bone, where you're basically getting rid of everything except for the X so that it rolls. But this is kind of useless. We shouldn't be using an aim constraint for a roll bone. We've already proven that we can make a better roll bone if we make our own that is specifically designed for it. We can make a much better one. So let's not use the aim constraint for that. And let's just ignore this and always leave it on all from here on. But we'll see what happened now. Now, one thing I also left out here is, well, we have a target, but it'd be nice if we had like a little line that shows you what's going on. So, we have our tools, and they've just been recently updated with a little special feature that allows us to add a shape, right? The plus shape here is for all kinds of shapes, bones and lines, and even I have some other things in here. But anyway, the most important thing is the bacon shape line, and it's just going to create a shape, and you can see it here already. It's created a line, and when I select the line, because I selected this first and went to that second, it takes the first one that you selected as where the shape is going to be attached to. So this shape exists on this object, which means whenever I select the line, it selects the object. It's not showing me that the line's selected on purpose because that would be kind of annoying. So over here, I have a new option called wire thickness. So we can go, let's say 5. It's just going to draw a much thicker line so we can see it, especially for these videos, because if it's too thin, the compression might not be great. In fact, I made sure everything is as easy as possible to see. And I apologize if it has a bit of a Fisher-Price kind of feel to it, but this is clear at least, so that's good. So, okay, so we use the up constraint with the scene up. I don't know why they use the term scene. They should have called it world up, but whatever. Because, they use the term world up type all the time, but I guess they didn't want to... See, it's confusing language, world up type. This is not what it means. The world up type is just saying what you're going to use as reference to match the up vector that you've decided is what it should be. It's bad terminology, so just know that, okay, so here we have, so that's good, but here's probably what what most people are seeing as a problem, because when they rotate the head, the eyes can maintain this kind of like upward, it's weird here, the eyes would be spinning. You want the eyeball, like that little green line, to follow basically the head at all times, right? So that doesn't make a lot of sense. So already, this is not good. So I'm gonna undo here. Oh, I'm gonna lose my line. It's okay. It'll take me 2 seconds. I just want to undo this. Okay, good. We're at a good point now, and I'm gonna just create that line real quick. It'll take absolutely no time at all. We're done already. Okay, so from here on, I want to go back to this, and I don't need to see this all the time, so boom, gone. Okay, so now we're going to use a different option. We still want the Y up as the up axis, but we don't want to use the world up because that's not going to work for a character that might be, on his side or so. You imagine the character's on his side, but the eyeballs are pointing. Anyways, it's going to get some freaky. This could get freaky. Okay, so scene up, not really all that useful for us for characters. Could be useful for something else, but not in this case. Object up, and you'll notice there's another object rotation up. Well, again, bad terminology. They probably wrote the object up and then said, oh, it's going to be referencing an object, but this time it's just going to use the rotation. What does that mean? Okay, so for the most part, just know that object up is the position, and object rotation up is using the rotation, meaning the axis, where they point in what direction. So this is ugly, but we're going to do object up first, and I'm going to unhide a little object that I have. Okay, so we can see that object. We can bring it in here too, just to see that we got it here, so we can see where it's being plugged in. And this is just a reference node, and I am going to copy this reference node's object or its name. I'm going to go Control C. Now, here's where these kind of scripts are very dangerous. Maya, instead of whoever made these tools, kind of decided to use naming convention because you can't select that one in tandem with this because if the main design for Maya was for the aim, like any constraint is, you select multiple objects that can affect the look at or the aim. And then the last object is the one that it will apply this. So you can have multiple things you can aim at and then have these weights that blend between each one of the targets. You could do it with the method that they use here, but there's other ways of doing that. It would actually be better to always be locked onto one object and then have that object constrained to position to others that you can blend between. So at least you have better control over what's going on. But anyways, that's neither here nor there really. The problem is, though, there's no way of selecting things in the right order to be able to include this other object. So they made it so that you just type in the name. And that's, in my eyes, this is awful. This is hideous. But it's also prone to problems. If you make you type something incorrectly, you're going to get errors. Also, if you have two objects that have the same name that are in the scene, this is not going to cut it. You're not going to be able to know which one it is. There's all kinds of problems that can show up with this. And what if you're using a reference file and it has that namespace? You're going to have to also include that in there. This is a mess to do, but let's just use it as best we can so that it works. And we're going to use the object up, not the one related to rotation, the object up one. And we're not even going to bother with this. This is always going to be on all, and we're not going to have any maintain offsets. Okay, so we apply that. You'll notice that it already changed a little, and it kind of reoriented itself to point to this object. And we can see that where I move this object, it does that. So to make things a little easier for us to understand what's going on here, I'm going to select this and this, and I'm going to, I believe it was this one, add a line. We're not going to bother with thickness because this one's not going to be lasting very long. This is kind of a weird way of doing it. So then you could parent this to whatever if you wanted to, you could parent that to the head here. And now when I rotate the head, that would determine where the eyes. So yes, this works. I mean, you want to do it that way, but look at all the. This is gross. Like how many objects are in here? This is ridiculous. And also then you'd be hiding this stuff, and then you have to have one for the other eye, and it's just not a great idea. However, the concept is good, and if you what you don't realize, you may not realize, is this is exactly the same thing as when we were doing the pole vector in IK. Maya called it a pole vector. I kept referring to it as an up vector. Now you understand why I was calling it an up vector, because it's exactly this, except for an IK chain. See, how is this different from the IK chain, where this would be the IK and this would be the pole vector? So now you know why I was referring to it as an up vector, because that's exactly what it is. Mathematically, it's the same. It's almost identical. So all right, so now we understand what the object up is, and so on. All right, so let's undo here till we get to the point where we don't have the constraint anymore. There we go. This guy, I'm going to pin it, and we might actually be hiding it in the next little bit. Once we finish with this, we're going to do an object rotation up. So here it's saying which direction on the object, like which axis do I want to use on this object to match the one that I have here. And in this case, I'll tell you what, I'll make it exactly the same as the y-axis, the positive y-axis. So I'm going to make it 0, 1, 0, okay? And I'm going to select them again in the right order. And I'm going to press apply, and it's got the right name. It's created the constraint again. It's correctly doing the split. You're going to notice that for the most part, this is the only output from the constraint from Maya. It's built in, so you can get this on any machine and it'll work. But you can see all the things that it's connecting here. It's trying to get a lot of information. These are all inputs because they're on this side. And the object that you're affecting with rotation is pushing a lot of data onto this side to be able to do the math for this. It's not just grabbing some of the information from the target and the reference node. There's some information, but not a lot. Anyways, so moving on. We did an object rotation up. So let's see what happened to this reference node. If I move it around, it does absolutely nothing, right? Because that was the other one, that was position. But if I rotate this, oh, look at that. It will match whatever the y-axis, what we said here, this y-axis, it will try to match it with this one. Now, again, I will repeat this so that we understand. It's not going to match it 100%. It's going to prioritize the x-axis always. The aim vector is non-negotiable. It has to point in that direction. The whole point of an aim constraint is that. But the up vector is more of a, let's say if I wanted the y-axis to point more in that direction, it's not going to affect it much. But if I rotate on this axis, yeah, obviously it's going to match it as best as possible. So the best way to describe this, if you don't want to go into the math any further, it's a suggestion for how the second axis is going to line up. It's going to prioritize. It's going to do two things. One, prioritize the x-axis or whichever axis you've determined as the aim vector, 100%, non-negotiable. Number two, it's going to maintain 90 degrees from. It's going to create an orthogonal transformation, which means the axis will be, each one of these little lines here will always be 90 degrees from each other. Okay. So that's all you need to know for now, if you're just interested in the Maya side of things. So you should be good to go. Now, the thing is, though, if you saw this video and you went through all that, and I was talking about a whole bunch of stuff that you probably at that point in time didn't really care for, and then you do your thing, you fix the problem, and then a couple months down the road, you hit the problem again, and then you see that this aim constraint thing, I can't remember. This is awkward. Like the terminology is not great. We didn't even do the vector one, but it's not really all that interesting. You type in the vector, and that's what it's basically another world constraint, but relative to a vector. Yeah, instead of using scene up, like the scene up and vector like 0, 1, 0 is exactly the same thing. So it's just that with scene up, you have no options. So with vector, you could change it. So in case you wanted, like, I don't know, off to the side, you'd use like maybe a 1, 0, 0. And yeah, I don't know why you do that, but anyways, vector is not really all that helpful for us. So I just kind of ignored it because it's kind of pointless. We already did scene up, which should have been world up, but then it gets confusing with the terms over here. Okay. So that's my point of what I'm saying. If you're coming back to this and you haven't seen this and you don't have my explanation where I explain in detail each and every one of these, then it kind of sucks to have to come back to this, and you might not, you might want to use an alternative. So I'm going to show you. I'm going to just get rid of the constraint here. And we're going to constraint this so that it works as best as possible. So maybe what we can do is not use this. I'm going to hide that. And we're going to actually use the head itself for an object rotation up. So if I turn on the axis, we can see that it's an x-axis pointing upwards. In the case of a rig in Unreal, that's kind of how it goes for every joint. Every joint will point along the axis of the bone. So the neck would travel along the x, and the head would travel along the x-axis. So in this case, what we're going to do is we're going to grab this, and we've called it head. So okay, object rotation up, and it's going to be on this one, and this is going to be called head. And I'm just going to select this in the correct order and apply. Okay, so if all is good, if I rotate the head, it's going to have that y-axis keep locked onto it. However, like I said before, priority is this, to have the aim and to have 90 degrees. So if I pull this way, it's going to try to keep the eye in the same direction as the x. So this is okay. Your character would be like trying to peek downward type of thing and maintain that eyesight, and it works. So that's fine. So with this, with the Maya setup, I think this would be like the cleanest way to set that up, and we're good to go. Okay, so now I'm going to unhide the that's the right. So we need this guy, and we need a target. We need the left. Okay, and we're going to this time create another shape line, and we're going to make sure it's nice and thick so we can see it in Maya and on the video. All right, so we have another eye here prepared, and we're going to be using something slightly different. So I'm going to just move that down. So let's get this guy and that guy, and bring those guys in. And then this will be hidden. We just want the eye on this side, and I want the target on this side because that's going to have an output, and the eye is going to have the rotation of value calculated. All right, so the only thing we're missing is to pin this. Might pin that too. I'm just pressing P while I'm in here. Good, we're good. We're all set now. For this eye, I'm just gonna then go and use the new Bacon look at. It's got a UI now. It's always been there. It's been there since day one. It's just that you had to connect things manually, and now, well, this is going to make things a lot easier. And you'll see that already this is much simpler. So that it should make things easier for you to use it in the future where you want to do this stuff. Okay, so in this case, let's just go straight to talking about what the aim axis is going to be. The aim axis is going to be x. Don't have to, write 1, 0, 0. And if you wanted a negative x, you just flip it. Then the up axis source will be, and here's the thing, I have a lot of features that are built into it, so you could modify it through the node editor if you wanted to go beyond this and do all kinds of things, like just like the other one, like the one from Maya. But for the most part, you're always going to be using these kind of setups. So I made it so that it's as easy as possible to use, and for the majority of the things that you're going to be using. So here's the up axis source, meaning the thing that where are we getting our information from? The target, the parent, or the world? I mean, yeah, that's not much more than that you need, really. Do you need a reference object? I could show you how to do that, and I'll do that next. But for the most part, with just the target, the parent, and the world, we're good to go. And that makes it very easy for selections and everything. So in this case, I just need my parent, because this object, if I press up on the arrow keys, is parented to that node. So I just need to use that object's x-axis, we said. And that's it. That's it. We're done. It's that simple. So what we do is then press apply, and it should have created, okay, I put it over here. And then we're going to open that up. You're going to see it's a lot simpler. And yes, there's a lot of things in here that we don't have, like the ability to blend between multiple targets. But that's where I find this is overcomplexified, something that we might need that needs to be calculated quickly and efficiently. And this is way more efficient for calculating that kind of stuff, because you're not going to be doing multiple targets. If you want to do blending of targets, it's like I said before, put the multiple targets and then have your I target, constrained to one or the other and move it around. So there's lots of ways you can do that, and I find putting it all in one in the one constraint is actually not the most efficient or easy to understand, because then you're playing with numbers, little values, and then you see the end result, but you don't see the actual objects that you have for targets, and you're not. Anyways, it's just this should be simpler, I think, and for the most part, 90% of the time, or even more than that, you're going to be using something like this, and you still have lots of options. And I still left a lot of other options too. So, like, you'll notice that I don't have the thing where you have to match the one axis with the other. It just does it in a certain order. And if you select this thing, you'll see that I have alternate solution. All that means is if you wanted the Z, it's going to go to Z. It all depends on what you picked as the aim axis. So basically, it's always going to take the next axis as the up. And if you don't want that, you just tell it to use the alternate one. So if you wanted the Y up, then your up vector would be aligned with the Z. If you do the alternate, it will go to X. Really that simple. And you can modify this on the fly. It's not something baked in. You can just change it anytime you want. So I think something like that is much simpler to use. I have other features in there. They're handy, but we don't need to worry about it too much. For the most part, it's already been set up. I've already connected the things we want, and it's going to follow the same logic as the any Maya constraint, where it takes into consideration the joint orient of the object and its local versus the world logic. So it's always calculating the local value that you need it for it to work. And here we already have a hierarchy, so you know that it's definitely working. And we should have something that looks identical. The worst one is going to be this one, right? So it is maintaining that up vector correctly. And both of these should work exactly the same. One is just much lighter and easier to understand. So that's why I would, not because I wrote it, it's because it's specifically designed to be more towards what we use it for. And it should be easier for you in the future. You'll know, okay, I want to use the aim axis as the x-axis, and the up axis, it'll be whatever you want it to be. You can use whatever reference you want. If you wanted to do that fancy stuff that we had before, you can totally do it without this interface. You can keep going. I'll show you. This is the node editor part that I was talking about. That interface is just there for convenience. So I made it so that it doesn't have absolutely everything in it. I made it so that it's just as convenient as possible, and it gets to what we need. If you really want to go with more details, then what you do is you go, oh, okay, this object that we had as a reference, I'll bring it back. Now it's back. I want to use that as my, like it's already been hooked up, but we can absolutely keep hooking things up here. So you'll see that it has a reference world matrix. So that's how I get around the world thing. So the reference world matrix just means, in this case, in world, not local. So I just grab this object's world matrix and I plug it into the reference. Now it is the reference, not the one that's in the world. I know that can sound confusing, and you can see why the Maya aim constraint is a little funky, because there's terms that are being getting mixed up, but hopefully you understand that this reference requires a world matrix, and this is called the world matrix on this node. If you don't hook anything up to this, by default it will have basically a nothing matrix, a zero rotation, zero scale, everything. That would be the equivalent of what the scene is, like the world is. I know it's confusing, but you should. I'm being very precise with my words that I'm using. So the world matrix is a lot of times the plug for most of these constraints, and it's just telling you that I want the world version, not the local version. And then now I just need the reference, which is this object here, and I need its world matrix hooked up to that. Okay, and so now now that it's part of that, I can change the how this is working. So instead of saying parent X, I could use reference position. So now you know. It's just like we had before, where we had the line. It'll always try to aim at this, but even if I move it this way, it's going to ignore that, because it has to maintain that 90 degrees. So it's still listening to the rules we set out. And if I change this again over here and just go, instead of reference position, use its y-axis, reference y. And that means now that wherever I rotate this, you'll get the same thing. So you can do exactly the same thing we did with Maya, but there's rarely a time that you're ever going to want to use that kind of stuff. So I didn't include it into the interface. But if you want to, you can easily just set that up here and play around with it. I have a couple of other things in there that might be interesting. Okay, I think we've covered those two quite well. And we've gone in depth on something that's quite simple. But the reason why this is so important for us is because a name constraint or a look-at constraint, in order to do it, you need to understand how a transform matrix works and why it's important. Okay, so I'm going to just head on over here and we're going to go to our web page, and I'm going to go to lexicon. And we're going to talk about the transform matrix, and then we're going to talk about something called cross product. Okay. So what you need to understand is that a transform matrix, and I'll just read it, it is the fundamental building block of all 3D software. It can contain position, rotation, and scale data. All gizmos and transform components lead to a transform matrix. Okay, and now I'm going to show you the link that it goes to. So what I don't go into detail here is that absolutely everything in your software, every single software on the face of this on the face of the planet, is using the transform matrix fundamentally at every level. Even to determine where the pixel is on your 2D screen is a transform matrix multiplication, where it's taking the three-dimensional information and then calculating where that is relative to the camera, and then the camera has to know where it is relative to your screen. And then it will do the two-dimensional image calculation to know where that vertex is on your screen. So transform matrices, the matrix for transformation is everywhere. And so this little equation I have here, and I'm going to go to that source that this is from Autodesk, right? This is Autodesk, the help form type of thing. This is documentation. They do this, they sometimes update this, but for the most part, I have this older version which hasn't changed. And you see, this is the key one, and I know that it looks like, what the heck? It's just a whole bunch of it looks like it's spelling some weird thing. the thing that you're looking at here is that this is telling you that for each thing that exists in Maya, position, rotation, scale, how your pivots change for, like I'll go through it in Maya in just a second, but everything is calculated with transform matrices. Each one of these is a matrix, and you have to be put in a specific order to get the final result that you see in Maya. And it does this every single tick, meaning every single time it needs to update and update your object. If it's animated, it does this for every in between, every frame, everything, all the time. It's calculating this all the time, so it has to be efficient. And in Maya's case, it's actually not too efficient, and it's missing actually one matrix that avoids the skewing matrix. But we'll see how that works out for us, because we might actually use it to learn and to understand why it's important to have an orthogonal matrix and why not having orthogonal is a bad thing. Okay, so if we look here, what you're going to find is this one's actually important. Rotation axis. It's telling you that the rotation axis X, Y, and Z has to be in this order. There's another part where it talks about rotation order. This is what the rotation order is. It's the mathematical order in which it multiplies the matrices. So if you have a rotation order that's ZXY, then you do the Z after the X after the Y. Meaning in this case, X is the first one to get. Actually, it's the other way around. But anyways, the X is dependent on the Y, and the Y is dependent on the Z, which means the X is also dependent on the Z. In the case of Z, it doesn't depend on anything. This is what we discovered. Remember, it's the order of rotation. Here it is. Here's the mathematical reason why that exists. Because when it comes to rotation, it's not like position where they're independent values that you don't have to worry about, because I'm going to for something that I'm about to show you. So it's not necessarily important to go through every single one of these, but I'm going to show you something for that specifically that will explain a little bit. So I'm going to do a new scene, and I'm going to create a polygon cube. Okay, so this is not going to work out for me because it's gray. Hang on a second. We got this little window here. It's off screen. I think it's this one. Let's just make it, I don't know, blue. There we go. That's good enough. All right. So now the default material is bluish, so we can actually see it. Now, the first thing I'm going to do with this cube is I'm going to go into the attributes, and I'm going to go into the section for the transform. So this is the first one is always, everything else after it is kind of like the child of this. And you can tell that I'm not making this up. If you display shapes, the vertices, the faces, all that gets calculated, and then it becomes child of the transform that it's connected to. But it's all in one package. It considers it one DAG node, really. But the transform is controlled by the transform node, and then everything else is child of that and follows along. That's the best way I can describe it. All your vertex information is going to be stored local relative to that transform. So this vertice over here, for example, it's going to be along the x-axis by 0.5, and then up on y 0.5. In the case of z, it's going to be, in this case, it's going to be a negative 0.5. So that's what that coordinate is, and it never changes. If I move this object, that vertice coordinate did not change. All right, because it depends on that transform, and that's why I'm making sure we understand this, because it's going to come clear in just a moment. Over here we have something called pivots, and I'm going to make it so that it can display the pivots. And I'm going to, in this case, for this part, I'm going to have to go into wireframe mode because they didn't make it so it's X-ray. It doesn't use an X-ray format, and we have here. This is the world, so we don't need the world. That's not real. That's just there to help us out because it shows you the value, but the local is what actually is actually doing the thing that in that equation that we saw before. So for the location rotation pivot, I'm going to move it up 0.5 because the cube is 1 by 1 by 1. So that means that for it to go from the middle to the top, it's 0.5. And then for this part, that's going to be minus 0.5, so it should be at the bottom. And there we go. It had a little update hiccup. But now what you're going to notice is that the local rotation pivot is like you think it's rotate, but it's actually position as well. You'll notice that my position gizmo now, when I select the object, is now there. And if I rotate it, it rotates relative to that point. So that little tiny offset is super important, because as we keep working, we need to keep that in mind. And if we scale it, it's going to be scaling from over here, not from over there, right? So if I was doing something like this, we're not, that coordinate didn't actually matter for the scaling, but now our rotation's all wrong because now we're over here. So now what? So this whole thing of pivot offsets and so on is very unique to Maya. They added these offsets to help modelers in particular. So let's just keep that in mind. So remember, one was called, let's see, what was it again? We had something called rotate pivot and scale pivot. So RP and SP. RP and SP. RP, SP. That's where they are. In that order, it needs to take into consideration that little offset when it's going to then add the keys and all the animation and all the stuff that you have for position and rotation. That's how it takes that into consideration. So when Maya updates, it has its thing of everything that needs to, all the matrices that need to be multiplied. Now, here's the thing. SP and RP is also down here, so we can actually see it. SP is this. Now, at first, you're like, I understand. Seeing a matrix for the first time, and you're going, what the heck am I looking at? It took me a while to figure it out. So I didn't just look at it and understand how it worked either. So just keep that in mind, that it takes time until you start to decipher this bizarre nomenclature or this bizarre formatting of numbers. And it's hard to wrap your mind around it at first, I know, to think that all these transform matrices, these blocks of numbers, are somehow controlling rotation and scaling and position, and somehow magically, if I just multiply them, it just works. It's a very strange concept. But let's just focus on the two that we know about. We know about the scale pivot, and here you have the three values. So you're going to notice that there's always this kind of pattern with most of these matrices where you have a 1, 0, 0, 0, and then there's a 0, and then there's a 1, and it just goes in kind of like you have the ones in a diagonal. All right, and in this case, we have a 4 by 4 matrix, and that's kind of already part of the puzzle. So you're already starting to piece things together, because you realize if this is this place that's being updated for basically what was a positional offset, and then over here it's doing it again for what was a rotational offset, but it's still a position relative to its center. Then you start to think, well, wait. You start to realize these three at the bottom must be always related to translation, and that's actually correct. If you were to make if you were to animate your cube 10 units to the right or on the x-axis, you would put 10, 0, 0. That would be the transform matrix that would represent moving an object 10 to the right. Rotation's a little bit more complicated, but I'm going to show you that it really, once you understand what else is going on here, it's really not that big a deal. So here's the thing. I'm going to use this. Desmos is a friend of mine. I love this website. I've been using it for years. And you can chart things and graph things very easily. It's lovely. This is a great tool to use whenever you want to do any form of math. You can even do all kinds of stuff with it, and it even has a section with, like, I went to desmos.com/matrix, and I'm going to create a new matrix. By default, it's a 2 by 2. So the way we say matrices is we say the row first and then how many columns it has. In the case of what we saw in Maya, it was 4 by 4, so 4 rows and 4 columns, and usually we saw this kind of pattern for the most part, and then some sort of change to it. We changed it somehow, right? This is known as an identity matrix, meaning a nothing matrix. It's nothing. There's no translation, there's no rotation, there's no scale. It is basically what your world or your scene matrix would be. So if this is a nothing matrix, then anything we change to it identifies how it changed and then transform from the initial. Remember how we said everything is relative to your parent? Well, the same thing is with the matrices. So your local value is always relative to your parent's matrix. That's its origin for its coordinate system. So in the case of a matrix, whenever you make this adjustment, you're basically showing it how it changed from the nothing matrix, the identity matrix. Okay, so here's another one that's really fun. Okay, now Maya, for the most part, always displays the 4x4, but to understand the matrix, the transform matrix, it's always best to do a 4x3. That other whole column that we just removed isn't really that valuable to us. We just need to remember that there was a 1 at the bottom, so it would make that diagonal, that nice cute diagonal. But from our perspective, when we're going to be thinking of matrices, we need to look at it like this. Remember, this is the nothing matrix, and we know that the bottom row is for position, right? So the thing that's interesting here is that we're kind of locking in on what's going on here already. We're starting to get an idea. Like if you think about it, this is a x. This could be x because it's 1, 0, 0. This could mean something related to y because it's 0, 1, 0. This is 0, 0, 1, so it's probably z. In fact, that's exactly what it is. So, and the bottom here is 0, meaning it didn't move. There's no positional offset. So just by knowing that, we can actually start understanding how we can construct a matrix and then use. At first, it's going to seem like magic because you're like, okay, somehow this packet of numbers, if I multiply them, what it calls multiply, is going to actually transform one thing with another. So let's say, and this is just to be, it's just so you can see exactly what's going on. Let's say we have a position on the x of 10 and a position of 20 on the y, like that's its coordinate on the y. And then I'm going to create a new matrix. Same deal. So I'm keeping it in 4 simply because we want to see the full thing and understand what Maya is expecting. Now let's say that we understand this whole thing with that was the position, and we know now that each one of these is related to it. And I'm just going to spoil it for you. But that direction is just like the aim constraint. This is why I'm connecting the aim constraint with all this stuff, because this is fresh in your mind. When we were constructing the constraint, we were saying which axis does what. The axis was being, in the case of Maya, was kind of like not very user friendly because it was asking the axis in this format. So x was 1, 0, 0. So in essence, the 3 coordinates is the direction in which the axis is pointing. That's it. So each axis has to point in a direction. So if you wanted to do, I don't know, like a rotation, well, this is a rotation. That would be a rotation because now your x-axis is pointing upwards, and the second row, which is your y-axis, is pointing where the x was pointing before. Actually, this is already this is not a great example because I've changed the wrong. Well, you know what? It's fine for this example. We know now that this is some kind of a rotation. There's the axis, the x-axis is now pointing upwards, and the y-axis, because it's the second row, is pointing in the other direction. So now we can go in here and go A times B. Look at this. A times B basically took this, and which has nothing but a position, and look what it did. It changed the values of the position. That's because you're transforming the positional data by the rotation, so it's where those coordinates would be if it'd been rotated the way it was. If I did this the other way around, B cross A, or rather B multiplied by A, you're going to notice you have the old position and that rotation. That's because in this case we took the one at the bottom at this point. It's the position is the position matrix being So it's basically just offsetting. It's going move this matrix by these coordinates. So this, whatever's on the right, is the thing that it will do to the first one. This object. This thing is being transformed by this one. Because we had it backwards before, where we had A times B, it's now taking this positional thing and rotating it. And that's why the value of the final position is different, because you've moved it, you've rotated it. It's in another place. Okay, I know that this is kind of weird, so let's just put a pot. Let's just let it simmer for a little while, and let's put a pin on it. So at least we now have an understanding, a little bit of an understanding of what a transform matrix is, and that the order in which you do these transformations is important. And you can do tests on your own for this one, just playing around with values and looking at where the axis is pointing, and just writing it down. In here even you can test it and see if you can predict what the values are going to come out in Maya. So I'm going to continue in Maya now. And we're going to go, okay, so at this point we've looked at this. Okay, so one more thing we need to do in Maya before we're done here, in this part of Maya, is we're going to create another cube. Okay, and this time I want to see the shape. Where was it? There it is. Okay, so this is the thing that we were talking about before, about the local axis. So what I want you to do is visualize this corner in particular. Okay, we're going to be fixated on this corner because it has the shape of our axis. It's 90 degrees. Each one of these edges is 90 degrees from the other one, and there's no problems, and that's not an issue. So now what I'm going to do is I'm going to grab this. Hopefully you remember this. Like, for those of you that were in my class, remember how to break Maya very, very quickly. You go like this and like this, so you make it a step. We still have our no problem there, right? Now all I'm going to do is just press shift, hold shift down when I'm doing this, and it's going to make clones. Doesn't matter. And now all I'm going to do is select, middle click drag, select, middle click drag, and it's just parenting the one at the top to the one above it, and that means that this will be at the bottom, right? It's the first one we created. And if I do this and I go rotate, no problems, right? Doesn't seem to be any problems. It's just what we'd expect, right? No problem. Now let's go somewhere around here and see what happens. Oh, things are getting kind of weird, right? I hope you, well, if you were in my class, I hope you remember this. And if you've never seen this before, welcome to how to destroy Maya really quickly. You can break it in 2 seconds like this. And there's other ones that we can do that can break Maya. And there's not much of a safety in this one. Like, there are other softwares that are a little bit better about this. For example, XSI is very good. It has something known as a shear matrix. Remember that equation list that we were looking at over here? Well, in the case of XSI, it has another one that compensates for any shearing, as we call it. Shearing is what we are seeing here. I've got another word for it that sounds like it, but anyways. I think there we go. You'll have to forgive me. I am in Linux, so sometimes the hotkeys are a little tough. Okay, so the other important thing here is that we were paying attention to that corner. So as you can see now, those corners don't look so good. They're not looking so hot, and they're no longer 90 degrees from each other, and that's what's causing this from doing this, because our transform matrix, when it was created at this point, has inherited this shearing from its parent. So what you'll probably wonder is, why is it that the first one doesn't have anything? And the answer is very simple. Everything is relative to its parent. What's the parent of this object? It's the world, right? It's the scene. So the scene matrix here hasn't been touched, hasn't been goofed with. But the very next one that I select will have problems already. See? Why? Because this one has been scaled, which means since everything is relative to its parent, Well, now we've got a wonky scaling, and now our axis, our space within that our parent is kind of warped because we can travel longer and faster on one axis than any of the others simply by moving on the, like if I go on the x-axis, that coordinate hasn't changed, remember? That's what I was getting at before. The coordinate still hasn't changed, and it's just showing you the result of changing the parent transform. So then it's showing you that this coordinate over here is the same as the one that's over here and the same as the one that's over there. They all have the same vertex information, the same coordinate. We never touched that. But the transform we did change, and we had an inheritance issue where one problem is being inherited to the next, and it's just getting worse as we go through it. This one would be the one that's the worst. Like, I mean, I'm rotating it and it's pretty flat. I mean, that's pretty freaky. It doesn't matter what I do, I will never get it unflattened from this for this guy, no matter where I rotate it. So you're starting to understand now, hopefully, the concept of subspace and how we create matrices. Okay. Now comes the last bit, and with what we've learned, we can actually get into the final stretch of this. I'm going to use this scene that I have here, and I've prepared this little scene. It may not look like much. I've got 3 vectors, and I've got something that's just there to really just show me where the center is, and we're not going to be moving it, although maybe later we might at some point just for illustration, but everything is relative to the parent. So if I leave it at the origin, it's as if it wasn't parented to anything, and we're drawing a line. I've got lines already set up so that we can see what this thing called vectors are. Like, it might be kind of fuzzy in your mind, and you're probably wondering, how does the math work? How do I construct these transforms and then write plugins to make this work? All right, but this is the holy grail of all rigging. The transform matrix has everything you need, and once you learn how to do that, then you can talk directly to Maya at its lowest level and be able to send it the information it needs to update. That's why I make my own plugins, because I'm able to do that. I can't really do that in Maya using scripting. You can script all kinds of things, but you can't just script things that update in every single tick, and the expression editor is quite terrible. So I'm not gonna be messing with that kind of stuff. So this is the reason why the Rigonomicon has its own plugins, and I will be going through the code in just a moment. But first, I want to show you what exactly cross vector or cross product is. So for this one, we're going to bring out the node editor. So we have vector. Wait, hang on a second. Let me bring that over here. Okay, everything should be crystal clear. Vector 1, that's the red one. Vector 2 is the green one. Vector 3 is the blue one. And we have a parent that's there, and it's just drawing the lines to help us out to understand what's going on. All right, so I'm going to just move this guy so that we know what we're doing. I'm going to put him to 2, 0, 0. All right, so it's further away than we're used to. Y is okay, and now what we're going to do is we're going to try to do a cross product with these two and see what happens to the third one. So this is the one that's going to be affected. And we've got these two guys here ready to go. So I'm going to do the simplest thing. I'm going to press tab, and I'm going to type vector. Cross. Yeah, look at that. Cross product. All right, and I'm going to press 3 on this just to open it up, and look at that. It needs 2 vectors as inputs, and it gives you a vector output. All right, so I'm going to take the translation from this guy over here, translation from this guy over here, and then I'm going to punch it here as the result. Well, would you look at that? It's kind of showing you where the Z would go, right? So here's an important thing that you need to understand. You also notice that this was a length of 1, right? So this is at the 0, 1, 0, and this was a length of 2, 2, 0, 0. It seems that the length also affects it. So we can do a little thing to fix that. So if we want to have perfectly a length of 1 vector, there's a little thing called normalize, and what we do is we just go in here, we go normalize, And what normalize does is it just grabs whatever vector you have. I won't go into too much detail because you just have to think that it's being made into a length of 1, meaning no matter what vector you have, it figures out the version. What it's actually doing is mathematically it's taking the vector and dividing it by its length. And you, believe it or not, the length is actually a Pythagorean equation. I won't go into that yet, because when you start realizing that the Pythagorean theorem has always been three-dimensional and you just didn't realize it because they just kind of put it's a squared plus b squared plus c squared equals the hypotenuse squared. That's actually the equation. We just never use the third component because all of our questions are always two-dimensional, so we just focus on the first two, on x and y. We don't really work on z because it's just too hard to draw that and it's harder to understand. But that it is legit. You can use it to calculate the length of a vector with that, and you take that length, which is a single number, and then you take the vector originally and you just divide each component by its length, and it will give you a normalized vector, meaning the length of that vector will be 1. So now you'll notice that this is exactly at 0, 0, 1. So now we have a very well calculated cross product. Now here's another little thing that you might want to keep in mind. Like what I was saying before, don't worry about the warnings. This is normal. I'm just flipping the order in which I'm doing this. What you'll notice is if I use the y-axis first and I do y cross x instead of x cross y, it flipped. It went to the other side. The order in which you do things matters. And I hope you remember the right-hand rule. Basically, the right-hand rule is being affected this to this. If you were to put your fingers and do that curling motion that I showed you, you would see that your thumb points in that direction. But if you start here and then rotate there, your thumb points in the other direction. So that's the easiest way I can explain what's going on here. And this is the fundamental building block for taking like directions and turning them into a transform matrix so that you can have your rotation value expressed as just directions of axis. And in the case of this guy, if I was like trying to build, like here's the other thing. I'm going to move it so you can see what's going on. What's going on though, the cross product as advertised will always take two vectors regardless of where they are. Like they won't be like I can make this so that they're not 90 degrees from each other. However, this the end result of the cross product is 90 degrees to the two others. This is 90 degrees to x, and this is also 90 degrees to y at every turn. So in order to create an orthogonal matrix, let's say that this x represents our aim, right? Like we said, non-negotiable. And this is negotiable. The y-axis is just a kind of an indication of where the up is. Well, we've got this one that's perfect, right? And this guy is also perfect in the sense that it's 90 degrees to this one. Right, so if that's true, if I were to make another cross product, let's say let's see, do I have? Yes, I do. If I had another one over here, and I bring that guy in, I'm going to lock all this in, and I'm in P, and I'm going to grab this guy and I'm going to bring him in. Now let's say we know that this guy works 90 degrees with this one at all times. We know that that's perfect. So if these two are perfect, if I were to do a cross product of these two, then this one would be 90 degrees to both of these, which means I would have an orthogonal matrix at all time. And I'm just using the up vector as a way of getting close to it. So it's going to show us where this should have been for it to be 90 degrees to these two. So let's do that real quick here. So I'm going to do cross. I'm going to open that up. So we said it was this guy. Now the order here is important as well. And I've got this translate goes here. And then I'm going to take this guy, open him up, and connect, translate. It looks like I need to do the opposite. So we're just going to flip that around. There you go. So now we also forgot to normalize it. So let's go and normalize it. Because if the length, it will actually determine the scale value. I know that probably went real quick, and you're probably like, what? So because we've been talking about rotation and position in the matrix and how it's represented, what you didn't know is that the scale is also included in the transform matrix, and that's done by the length of each axis. So the length of this right now would probably be in the vicinity of about 2. So that means it's scaled to 2, but we don't want that. When we're building it, we're going to do this kind of thing. Oh, hang on a second. Yep, there we go. So now it's proper. Now it's going to be a length of 1. So if we look here, all we'd have to do is fix the x-axis to be a length of 1 at all times, and you have your orthogonal 90-degree matrix that has now a way of having an up vector, just like it was doing in the constraint. And then all we're doing, at the end of the day here, it's just 2 cross products, a bit of normalize here and there. That's it. And you've constructed your transform matrix. And then the rest is just converting that value so that Maya understands it. So in the case, so now I'm going to go into the C++ plugin to show you that what we just did right here is exactly how this is done. So yeah, that's constructed from these two. So I'd have to, like, if I brought this guy to 1, 0, 0, and I brought, because this is the up vector, so I can bring him to 0, 1, 0. That should be an identity matrix right there. Perfect. Every axis is pointing in the exact, and because, well, we manually normalize this, because if we start we're not going to see the difference at this point, because it's okay. So anyways, so all is good. We know exactly what we're doing here, so everything is perfect. Hopefully you understand this part, because now I'm going to do the final bit, which is going to be looking at the code. And I know I'm doing a lot in this video. We've covered a lot of ground, and hopefully you're still with me. This is if you can handle this video and you catch even a glimpse of some of the things I'm showing you, it will help you for the future video that I'm working on, and a future series of videos, which will be much more in depth and have a lot more going on. But what we're doing right now it's just going to be a variation of what we're doing right now. So I'm just introducing it in a way that you can let it just simmer. So for example, this is the actual code that I have, and it's open source. You should be able to access it. It's part of the BaconStrip GitHub repo that I have. So you can just go in there and you can grab the code. I'm just going to just show you, like, I actually modified this manually today. Not this one, but one of the plugins, because I wanted to be able to change the width of the shape line that I had. And I just added it, and now I'm going to pass that on to the Mac and the Windows version as I make a new version for Maya 2077. 2077, that's the cyberpunk Maya. Okay, so bad joke. Okay, so moving on. Like, this code here, this is the Bacon Look At. The thing that we just saw, where we had those axes, this is what it actually does. So you never start from scratch. You never ever start from scratch, because Maya is expecting certain things to be in a certain way using its what we call libraries of code. So you can then go to that library and say, I want this function from that library, so I can access the information. And it has a whole setup of its own. So you can't just start writing you have to adhere to its standard. And the best way to do that is to download the dev kit that goes with that year, and look at the dev kit and then go, okay, here are some examples. And in these examples, I will learn what it's expecting and what format for it to work. So in this case, it's something that's going to create a shape. Well, actually, no. So this is the bacon look at. The shape was the thing that I modified, but this is the bacon look at. So this is the thing that just does a calculation, a constraint, for us to be able to hook up just like any other constraint in Maya. It's exactly the same as what I'm doing here is exactly the same as what every single constraint in Maya is doing. And in the first part of the actual code, I'm just going to go through the parts, the sections, very roughly, because I'll go into detail in another video. But I just want to introduce it to you and show you the logic that we just, where that logic exists inside this plugin. So I'm going to go just show you the start of the plugin and the end of it first. So the first part tells Maya which libraries we're going to need. And for the most part, you're just going to be copy pasting. Once you've created one, you're probably going to be using them again. You copy paste these, and these are like, all right, I'm going to need Maya's tools for calculating an angle, or I'm going to need Maya's tools for Euler rotation, because it has its own methods for internal methods to convert Euler to let's say to quaternion and so on. But you also need the quaternion library to be able to do quaternion math and so on. And I'm going to call things from that library to be able to calculate things. For the most part, you just bring in what you need. And I even have my own include, which is called bacon math, which is just a thing that has a whole bunch of functions that I've written that help me tremendously to optimize results. And then the next section is going to be, this may look like gibberish to you, but once, just like the transform matrix, once you start understanding the pattern and the formatting, then your brain starts to understand what each section does, and then you just go in and modify the sections that you need in order to get the result that you want. So in the case of our bacon look at, we need to know the targets world matrix. We need to know the objects world matrix. We need to know its joint orient. Remember, we need to calculate the local value that the final local value. So we need to remove the joint orient from the joint orient rotation from the final result. And then we also had stuff like what direction the aim is going. And this is just creating like the placeholder, like a box, to say there's going to be data in here, and this data has to be in this plugin of ours. So when Maya saves a file, it's going to look at this first, which is called the ID, which means this is the number that identifies this plugin, and says, it doesn't look at the name, thank God. For its plugin, it uses an ID, a number, a hexadecimal. And actually for bacon, for all bacon strip stuff, I actually officially got these numbers from Autodesk about 10 years ago. And it's a group of numbers that only I can use. No one else can use this. So if there's a plugin that interferes with what I have, that's not accepted by Autodesk. They have to change their number. They have to adhere to Autodesk's there's reserved numbers for everybody. So I'm just using, every time I create a plugin, I just take another one of my numbers that are assigned to me by Autodesk, and then that number becomes the identification. So when you load a scene in Maya that has one of your plugins, it's going to know by its ID, and then it's going to know, because of this, it's going to know that it needs to have this information. It has to have this data. If there's something missing, it's going to complain, and it will crash, and it won't load correctly. But it won't crash Maya. It'll just say, whatever you have here, I don't have it's not compatible. And over here we have another section, which is this exact same thing, but just trying to be more descriptive of what kind, like, there's can only be one Maya type ID, and the rest are all called Maya objects. Might be a float, might be a Boolean, might be a rotation, might be, who knows. So you can make Maya objects, and that you're just defining it so that it holds it. Now I'm gonna zip down to the bottom half. Now this whole section, this is where the majority of it exists. These are the inputs and outputs, and the names that we just defined have to be told what kind of thing it is. So in the case of, let's not take here, aim axis, okay? The aim axis is going to have X, Y, Z. Remember the drop-down list? You can only pick X, Y, or Z. and it's going to be referred to as aim axis, and you can have a shorthand which is AIMA, and the default value is 0, which is the X field. You can change that. It's not going to change the actual number that's attached to it. So when you save your Maya file, it will know that I've stored a piece like that little bit of data has to be in this format, so that it has basically an integer that goes to this list and says which one you have selected, and that's what it does every time it starts. And all of these at the bottom are just for everything that you plug in or output. It gets included. Now, I'm not going to go too much detail here. It has to do with updating Maya, telling it, okay, if you updated this one of these values, I want you to calculate the end result again because something was updated that was important. So this is the dependency, basically, what the dependencies are. So any one of these inputs, if you change at any point, like its value changes in any way, it will go and update the final result. That's all it's doing here. And then the final little bit here is just telling it is a plugin, and it's called Bacon Look At, and it's part of the Bacon Strip plugins. And that's it. So all of that leaves you with this little section here in the middle, because this over here, don't worry about it. It's just getting the information. It's pulling the data out and creating variables that we can then use to access what's actually going on. And you're going to notice, I'm not going to go into too much detail. Again, I'm just trying to get you to see how a plugin is constructed at the code level, so you can start seeing that there's no voodoo here. This is all everything's on the up and up, and I'm just following exactly the architecture of Maya, and all my plugins are no different than the ones that are in Maya, and I'm following all their conventions and trying to optimize as best I can along the way and make it user friendly. But here, this part, the part that you're probably interested here has to do with what you've selected to know. It's going through some mental gymnastics to figure out which axis is pointing in which direction and which one is the X, which one's the Y. That's all it is based on your selections. But the most important part is down here. This is the solving part. So from here on, this is pretty much all the math that it's doing. This is it. This is like all that stuff we just saw. Comes down to this little section here. And it's doing... You see this little symbol here? That's the shorthand or the symbol that we used for a cross product. When I put a vector with this little symbol that looks like a little chapeau, a little hat, it means it's going to cross product in that order these two vectors, and gives me another vector. And it's just like we did in that last explanation. We took the x-axis, we took the y-axis. These are our inputs. The y-axis was just a suggestion because then we created the real z-axis, and then we had an x and z that were perfect, which meant we could then generate the perfect y. And that's just two cross products, and with a little bit of normalize here and there. You'll notice that I'm normalizing like this. That's it. So you're just doing cross products, normalize, cross product, normalize. That's pretty much it. There's not a lot going on. It's actually really, the aim constraint is probably the easiest one to put together, because and what you're doing for the aim constraint, you do it for absolutely every single other constraint that exists. You're always using the transform matrix at the end, and just about, and then you're just converting those values to an Euler XYZ that gets plugged in to your output, or it's a position that gets output, or a scale, or whatever it is that you need it to be. So hopefully I've just introduced it and we've just looked at it very briefly, but this hopefully has whet your appetite to know more. And I will be going through probably a series of videos that I have planned to be able to get us to the next level of understanding, and for rigging, to really get to that place where we're just building whatever we feel like, and do whatever we want. And that's, I think, a worthy place to be. Like, it's a worthy goal, and I hope most of my students, I hope you'll come along with me on this one, and at least be interested in looking at it a little bit, just like this video. If you like this new format where I'm going more in detail, so I start the video off with the simple stuff, and then I move my way into the more complex stuff, and it just keeps going. The next couple of videos should be interesting for you that I'll be building, where we're going to go into more detail on some of this. Or if you prefer, just let me know in the comments if you think that maybe you'd prefer more application of plugins that already are there, and just knowing how to build things with explanations behind, to explain to some extent how this stuff works. All right, so hopefully you'll let me know what you think.